All right, shall I start? Okay, good afternoon, everyone. Again, today we're gonna talk about, discuss about the project, about project 4b, XV6, and it's basically based on what you have done on p3b, right? In p3b, as you can remember, which I think it's the most difficult one, you basically rearrange the virtual memory layout. And for this project, you are basically using the memory layout on the left, which we have already provided you the code. So I think you already found that. And now you should start from this virtual memory layout and then try to implement the threads in XV6. Okay? And the only difference for this start point with what you've done in p3b is basically right now the stack of a process is only one page and it will not grow for this project. So it's just a fixed size of one page. And then, as you have read through the instructions, we will basically put the stacks of different threads down below the process. And we will leave a guard page, which is free or unmapped, like every other page, right? Just looks like this. And the heap, code data, this that does not change. So this is basically what the virtual memory layout will look like before and after the p4b. Okay. So today we'll just focus on how to implement threads in XV6. So I think Gerard have already told you the difference between process and threads, and there are still a lot of similarities. So basically, what is a thread? So I think from the XV6, you can just treat thread as a process which shares the code, data, heap, and file descriptors, etc., with the parent process. And the only distinction is that the stack, right? Every thread has its own stack. So other than that, I think basically all the key points are shared across threads and the parent process. Oh, by the way, stack is separate, but another important set of thing is separate. What is that? Besides stack, do you remember that? Right, exactly. Registers like ESP, EIP, EBP, right? Something like that. They are very different. And today we're just gonna buy the tool, which I think most of you have used, the GDB and also the OBJ dump, to look exactly how the register move and change across the whole process. Okay, so but other than that, all the other resources are shared. So from the perspective of the scheduler, the thread is also placed into the p table, right? So you can just for the scheduler, it does not know exactly which one is thread, which one is process. It's just scheduling it like in a round-robin fashion or in a multi-level feedback queue as you implemented in the p2b. Okay, so for the perspective of scheduler, thread and process is identical. Okay, so if they are identical and they are placed into p table, which means first they will have a PID, right? So I think also mentioned in the instruction, there will not be a TID or thread ID in this project. It's just a PID. And it will be placed into the p table, and the scheduler will just scan the p table and schedule either the process or the thread. Okay. Okay, and then the key function or the system call we're gonna implement is called clone, and it takes in 2 arguments. The first one looks very I'm not sure if you're familiar with that, but it looks like a bit complicated than the usual one. For example, more complicated than the second one. Okay, let's just look at the second one. The second argument is essentially a void pointer or general pointer. So it basically will be fed in to the function or the routine that will be called by a clone or the thread. Okay, and the first argument is essentially a function pointer. Okay, and here is just the type of the argument which is associated with arg. So essentially, when you call clone under the hood, this is system call, and a new thread will be created, and it will be placed into a P table, just like a process. And meanwhile, it will execute a function, this function, which is the start routine, with the argument of void pointer, of void arg. Does that make sense? So it's basically create a new thread, place it to a P table, and then execute this function. That's it. Okay. And actually, this clone function is just analogous to our real-life Linux API, which is pthread create. Okay, so if you look at the menu here, so of course, pthread create has a lot of. Can you see that? Okay, so pthread create takes in like 4 arguments. We don't care about the first 2. So the last 2 is essentially the same with our clone, right? So the first one is a function pointer, start routine, which is FCN for this project, and then an argument. So when you create this thread, the start routine will be executed and taking the argument arg as the argument of this function. Okay, so okay. So before we go into the clone in detail, we have to have a better understanding of the x86 calling convention. So what is the calling x86 calling convention? I think if some of you take the class of 354, I think you have some basic knowledge of it, but in case some of you don't, or in case you forgot, let's just refresh our memory step by step using the GDB. So essentially, why are we interested in this part to finish the project 4b? Is because again, this function, so clone is a system call, and FCN is the start routine. It's actually just a function. So if we want to execute this function, it's actually a function call, right? So we have to follow some protocol, follow some convention, and then call this function, and then return by this calling convention. Okay, so now let's just, for a very easy example, let's just look at our first demo. So this is just a piece of code which is very simple. So it's in just a user program in x86. Okay, so here we have a main function, and we just print something out, and as an argument here is just another function which is a worker. So we call another function worker, and then just do a very simple arithmetic job, and then return, and then we print out, and then we exit. Okay, so it's very easy. So if we go to use our tool, which is the obj dump, and so all the user programs, once compiled, the executable will not be in the bin or something, right? It's not like our usual. It's placed into the folder called fs. So the executable is in fs, and here we have demo 1, and we dump, and we have the assembly code. So this is the main function, and now we have this printf. and then we do a bunch of things. And this is the worker. Worker is down here. Okay, so now I want to use GDB to help us step into this line by line to see what is going on the, under the hood. Okay. So let me just. So this is the assembly code. So the C code, everyone is remember that, right? What it's doing. So just in the main function, we just print something out, and as the argument, we have to call worker, and then worker return, and then we print and exit. Okay, it's a very easy one. I just show you the assembly here, and here we just open the GDB. Okay, I need another window. Here. Okay, so this is GDB. And by the way, if you just open GDB and try to set up a breakpoint at the kernel function, that is totally fine. However, if you want to set up a breakpoint at the user program, it's kind of tricky. So in case you still don't know, I'll show you here. You have to add symbol file. And now this file is called fs/demo1. And that's not all. If you enter, it will says the address is not found. So because this is the user program, as you can remember, we have already in the virtual memory, we have already have 2 pages unmapped, right? So the starting point of the main function is at the address of 0x2000, right? So we should have a starting point here. And then we accept, and then this file, this user program, the executable is visible to the GDB now. And now you can set up the breakpoint into this main into the demo 1. So we just break. I think which line are we interested in? Sorry. So here we probably just want to go to line number 9. Okay. Okay, so now we should run, continue. Okay, here we go. I'm not sure if, okay, this one should be correct. So you can see here, what does this, can you see that? 0x2011. What does this address mean? You can just connect to this guy with the obj dump or the assembly on the left. Can you locate where this is essentially the address of the instruction, right? So it should be here, right? 2011. Sorry. Okay. So the assembly is sub. So we just basically subtract 12 from the ESP, right? So it's just this. Sorry, it looks slightly different. Hold on a sec. Okay, sorry. I think now it's. Okay, so this is the QEMU part. We should run demo 1 first. Okay, now on the GDB, we should continue. Okay, now we got it correct. So it should be, so still this instruction, which is corresponding to this guy, we should subtract 12 from ESP, right? Okay, so basically the ESP pointer should be shifted down by 12. Okay. So if So in GDB, you can also inspect the registers. So how to do that? Then just info register. Like if you want to see ESP, which is the stack pointer, then here we go. This is the address of the ESP. So as you can see, it's almost very close to the user top, right? The hex of user top is A followed by 4 zeros, right? So here is the ESP is very close to the user top, which makes sense, right? If you think info register is too long to type, of course everyone thinks so. We can just in short we can just type I and R for the first letter, and ESP also works. Okay, so this is a very powerful tool. GDB you can find a more useful. So when I try to use GDB at first, I only know very rudimentary instructions, but later I found there are a lot of more interesting things or more powerful things to discover. So, and we can also look at the EBP. Okay, so it's slightly above. Okay, so when I say above, I mean higher address. Okay, below I mean lower address. Okay, so it's slightly like 8 above the ESP. And we can also look at EIP, which is the instruction pointer. See, it's exactly 2011, right? This is so it means that makes sense, right? We are running at this instruction, so it's of course the EIP of course points at 2011. Okay, so I think this is the basically registers we're interested in. Oh, one more thing is the EAX. Okay. Oops, sorry. One more thing is the EAX. I think EAX is right now is 0 because there are no. We are not doing any calculations right now, so there's EAX is empty. But later we'll try to look at it. But first we are more interested, especially interested in ESP. Right? Okay. Okay. Now we will want to go to the next step, right? From 2011 to 2014. If you type N, which represents next, it will actually, because currently it's at the printf, the C code, right? If you type N, then it will go to exit. So you just missed a whole bunch of things we're interested in. So you cannot use N. If you use NI, then it means the next instruction, which probably be okay. But right now, we have to call worker, right, before we finally finish printf. So the best way is to step in. So step into a next instruction. So if you want to step from 211 to the next function, to the next step, you should use SI, step in. Now we are at the next. We are at the next instruction, which is 2014, right? Okay. So for this instruction, we basically push the number of 3 into the stack. Okay, so for a better demonstration, I have a scheme here. So this is originally, I think this is instruction for 2011, okay? So remember, ESP is here, EBP is here, EBP is 8 above ESP, okay? This is our initial state. Next, okay, sorry, I think so initial state is like this, and then we subtract 12 from ESP. So this is corresponding to this line, okay? And now we push the number 3 to the stack. Does that make sense? So this is actually the end of the stack, right? This is where ESP is pointing at. And now we push the number 3 to stack, which means ESP is now pointing here, and the value of this address will be 3, right? This is what push is doing, okay? So we should think of push as this way, okay? We push things from here, we pop things down here. Okay? So we push 3 here, and the ESP will be pointing at this address. And what's next? Okay, so we go on SI next step. Now the number 3 has been pushed into the stack. If we look at the ESP right now, it should be 9FFC3, okay? And it's just the same here, right? It's pointing here. And you can also dereference the address if you like. You can also dereference the address, which is, you can just do this way. 9FFC0, and then it's 3, right? Okay, which means 3 has been stored into this address. Okay, now let's move on. Okay, what is this step doing? So it's the instruction is pointing to the EIP is now at 2036, but we were originally at you still remember we were originally at 2014, but why are we jumping to 2036? Sorry, we were originally at 2016 here. So remember here, because in this step, the assembly says call something. This is calling the worker function, and the worker function is, where is it? Is just at 2036, which means now our EIP should move from 2016 to 2036, which means we want to call worker. That's exactly what it's doing, okay? So it calls worker and it's at 2036. It's exactly the address of the worker here, down here, okay? 206 is down here, the beginning of, if you don't believe that, we can just check our EIP, which is exactly 2036, okay? And now, let's go back here. So this is push, okay? Okay, now we call 2036. And this is, so originally it's here, ESP is here, and we call something, ESP moves down. And what is this address? Let's go back to the, sorry. So when you, let's see. Okay, so let's just print out the address of, so let's see where is ESP now. Okay, ESP is at 9FFBC, okay? So it's just here, 9FFBC. So let's see what is stored here. Okay, so let's just dereference, okay? Dereference this address. Sorry. Okay, sounds like a hex. Okay, so at this address, which is ESP is pointing at, it stores a number called 0x201b. What is this number? Can you find something here? Okay, let's just search, okay? 201b. Aha, here, right? So let's try to clear our minds. Okay, so originally we are at 2016, right? And in 2016, we are calling the worker, which is at 2036. And the EIP now points to 2036, right? But meanwhile, at this address of 9FFBC, which is the ESP is pointing at, we stored another address, which is 201B. And 201B is exactly the next instruction of 2016. Why are we storing 201B here? So let's go back here. Okay, so this is a more diagram. Okay, so no, let's again walk through it. Right, this subtraction, that's fine. That's making space for the stack. And now we push 3 here. Okay, everything is fine. Now we call the worker. Okay, the worker is at 2036. And now the EIP will point to 2036. But meanwhile, we store the address of the next instruction into here, which is 201B. Anyone have an idea? Why are we storing this address here? Sorry, say that again?
Because it's the return address.
Okay, exactly. This is just a return address. Return. So it's basically because we are calling worker, right? So finally, we will return from worker. So this is exactly the next instruction after we return, right? Because if you don't tell the assembly or the code if you don't have bookkeeping this address, then when it returns, the instruction, the EIP will not know which step what is the next step, right? So we have to store the return address here as long after we return from the worker, which is the function we call. Okay, and later we'll see how it works. Okay, now we just store this return address here. Okay, now let's go back. So where were we? We should add, now the EIP should point to 2036, okay? Okay, let's move on, SI. Now it should, okay, the next, which is 2037. Okay, what is done in 2036? Just push the EBP. What does it mean here? We basically store the value of EBP into the stack and push into the stack. Okay, so after we call, we push. Okay, so originally EBP is here, right? And now we push EBP to here. So EBP has a value, is at address of 9FFD8, right? And we just store this value into the top of the stack, which is here. And now ESP is pointing here. This is what push does, okay? And then, sorry. What's next? We just move the ESP to EBP. So basically, it's not moving ESP above to EBP, okay? It's just update the value in EBP to be ESP. So that's exactly what's done here. So originally, EBP is pointing here, has got a value of FFD8. And now we move the value of ESP, which is 9FFB8, to EBP, which means EBP now will point at the same place with ESP. Why are we doing that? Anyone has an idea? So we are in the worker now, right? The function. So the function itself is like, it has its own stack, something like that, right? So the EBP is just like the start of the stack. So because we're running a new function called worker, which means the EBP should now point to the base should change. So when EBP and ESP are pointing at the same place or the same address, that means the stack is essentially empty, right? So now the stack is only, because they're, okay, so let's go back. So for example, like this, what is the stack? Where is the stack? Or what is the range of the stack right now? It's just between EBP and ESP, right? EBP is just the bottom of the stack, and ESP is just the top of the stack. When you push, then you store number at the top of the stack, and ESP will be updated, right? But now, ESP and EBP are pointing at the same address, which means the stack is empty. Okay, so that's exactly what it means. And why we want to make this stack empty? Because we are in a new function that is worker, and it's got the stack. We haven't pushed anything in it, so it should be empty. Okay. Okay, now let's go to the next instruction. So here, what it does. So after we move ESP with EBP, so what does the parenthesis here in assembly? Does someone have an idea? Okay, so we basically add 8 to EBP, right? And then? Exactly. So the parenthesis in the assembly is, it's got a special meaning. So for this, the 8 with the parenthesis of EBP, it's just like in C, we do the pointer arithmetic, and then we dereference the pointer. So essentially, it means we add EBP with 8, we got that address, and then we dereference that address to get the value. And that this is doing. And then we move that value and store it into the EAX. So in the diagram, we move. So originally EBP is pointing here, right? And what is EBP plus 8? It should be here, right? And then we dereference, we get the value, which is 3, right? This is what we pushed 3 here, right? And now we want to get the value of 3. And then we move the 3 into EAX. We store 3 into EAX. That is what it's doing. Okay, now let's, so again, let's just look at ESP. Okay, so it's an EBP. Okay, they are pointing at the same place. And now let's try to dereference 9FFB8 plus 8, right? We got 3. And now what is EAX? 3, because we store it into EAX. Okay, everything makes sense. Okay, now let's move on. Okay, we pop. So it's 203F, which is here, okay? Probably I missed one step. Yeah, it's here. Here we add 1 to EX. That everyone is very familiar. Okay, that's fine. Okay, now let's move on to the next, which is pop. Okay, now EX as expected should be 4, right? Okay, that makes sense. And now we pop. What does pop do? We add 1 to EX. Pop just means we just get the value of the stack of the ESP, right? ESP is pointing to the top of the stack, and we just get that value, and ESP will move down. That's basically what it does. And pop the popped value will be stored into EBP. That is what it's doing. So, okay, originally ESP is here, and then we pop, and ESP will move up, right? ESP move up, and the popped value is exactly this guy, right? And this guy will get stored into EBP. What does it mean? EBP will just reset, the value in EBP will be reset to this popped value, which is exactly its original place. So what does pop do? Pop is essentially popping this item, and ESP will go up here, and then the popped value will be stored into EBP, which tells, hey, EBP, you have your old value is here, so you should return here. Why we want to EBP to go back here? Because we are going to return from worker, right? So that's exactly what it's doing here. Okay, next. Return. So what does return do here? Return essentially, ESP will pop again. Okay, now ESP will point here. And the popped value is this guy. Still remember this one? What is this value? The starting address of the worker should be 2036, if I remember correctly, right? This, right? So it's not exactly. Return, right? This is the return address. So we are, because here we have already pushed the return address here. And now when we return, we know exactly where we are going. So that is why we should store the return address here. And when you look at the assembly, so return address is just 201B, right? So we get this return address so that when we return from worker, we know exactly what's next. Okay, so we then know, okay, now we're at 201B, we should go on, move on to the next. So that's exactly what's the return address for here. Okay. And after we return, so now I think we are at, yeah, exactly. Now we return, the EIP points back to the return address, which is 201B. Okay, so what does 201B do? It will add 1 to the, sorry, not 1. It will add 16 to the ESP. So in the diagram, originally ESP is here, and we add 16, which is 4, right? And then ESP will point here. Yeah, ESP will point here. Now EX is 4 already. Okay, what's next? Then we again subtract 4 from ESP. Then ESP will move down. Okay. And then, okay, we'll push EX to the stack. So subtracting ESP here, subtracting 4, it goes to here, FFCC. Then we push EX to the stack. So still remember, EX is 4, right? And then we push EX to the stack. So right now, 4 is stored here. Why do we push EX here? An idea? What is 4? Where does this 4 come from? Let's look at this. exactly, we return. And this is the 4, so arg is originally 3, right? 3 plus 1 is 4. 4 is exactly the return value. So, and we have already stored this return value 4 to the EAX. That's why we want to push this number 4 to the stack. The reason being, because we want to run printf, right? Printf will take this return address. So that's why we want to push this return value to the stack. Okay? So I think we are here. So we push EX, which stores 4, to here. And what's next? Okay, we'll push another weird address to the stack. Anyone know what is this for? Okay, let's try to search 27. I don't quite remember. Yeah, it's kind of different, but yeah, because okay, let's see this. We didn't find anything. So it looks like it's not an address somehow in the assembly. Then what is this address for? Let's try to print something, right? Print. So this is this address. We just want to dereference it to see what on earth it is. Okay. Looks doesn't work. However, /c means to print a character, okay? Now we'll print the second character. Okay, that is 1, what about 2? A. Oh, sorry. I. Does that ring a bell? N. It looks like it stores a string, right? Where does string come from? What does this string come from? It's exactly here, right? So this is a string. So for that weird address, it just stores the string here. So why are we pushing the string or the start of the string, the address, to the stack? Because again, we want to call printf, right? We have to push every argument into the stack so that we can finally call printf. So we first push 4, which is the return address of worker, and then we push the pointer pointing to the address of the pointer to this string. So you can expect what's next. And then finally we push 1 to the stack. So let's see if it's true. Exactly, right? We push 1 to the stack. So, okay. Okay, so this is, we push, okay, this address is slightly different. The reason is that I changed the string, but I didn't update it in the slides, so the address here is slightly different. But anyway, this is just the address of the string that is going to the argument of the printf. And now we push 1 to stack. However, originally at this address it was 3, but here we kind of override it. Is that fine? So if you still can remember, 3 is actually the argument of worker, right? Worker 3. And at that time, we push 3 into here. And now we push 1 here. It kind of overrides the original value. Is that fine? It is. Why is that? Okay, again, because as I mentioned, the scope or the range of the stack is just between EBP and ESP, right? And now EBP, ESP is just at that chunk from 9FFC8 to 9FFD8, right? And we push, we grow the stack, and here 3 is actually already out of the range of the stack. Although the value 3 is here and you can still access it, you can still dereference it, but from the perspective of the calling stack, this value is actually doesn't make any sense anymore because it's already out of the scope of the stack. So whatever value is that will not be able to dereference it. So, and we also didn't clear it. That's fine. We just leave as this until our stack pointer, our stack grows such that it overrides it. That's totally fine because 3 here is already out of the scope of the stack, so it doesn't matter. Okay. Okay, now we have already pushed the 3 arguments of the printf. And what's next? If you don't see the assembly, can you expect what is next after we have already pushed the 3 arguments of printf into stack? Okay, call. What does call do in this diagram? Sure, we should call our printf. What actually call does here? This function will return, right? Printf will return. No matter it's a void or we return int or whatever, but finally it will return. As long as it returns, we should just push the return address into the stack, right? So we will essentially push the return address of printf into the stack. That's exactly what does call here do. So let's check if 202e is the return address of printf. (202e) here, right? It's just exactly right to the call, okay? So when we call printf, we jump to the address of 242f, do whatever printf does, and finally when we return, we'll go on from 202e. Right? That's exactly why we need also push the return address at the stack. Okay, so I think we are kind of, okay, this is, okay, now we call, okay, then we'll do whatever printf does. Okay, that's probably out of the scope of this demo. I think we've done because whatever printf does, we're not interested in. But after that, we'll just finish printf, and then you see this is exactly the return address, 202e. And we'll continue and exit, yeah, and system call, whatever. So I think I finished the first demo, but looks kind of probably tedious. But I would like just to go through again from here briefly to refresh your memory, okay? So at the very beginning, we just had this state, which is ESP and EBP, and this is just the scope of the stack, okay? And then we subtract 12 to ESP, which means we need to make space because we want to try to push arguments here. If the stack is so small, then we'll just, you know, like kind of out of boundary, right? We're out of space. So we want to make space so that we push the ESP down. Now the stack is, the scope of stack is of this size. And next we push, right? Push the argument of worker here because worker has only one argument, so that's the only thing we need to push. But because worker will return, will, when we call in this assembly, we'll at the same time push the return address, which is the next instruction after we return into the stack, okay? And then we'll push EBP into here. The reason is that now we want to call worker, and the base of the stack will change, right? It's no longer here. It will go down here so that we have a new stack. So we'll remember what the old EBP is, such that when we return from worker, we will restore our state. Okay, and okay. Now the stack size is 0 because they're pointing at the same address. Okay, and then we do this parenthesis, which means the pointer arithmetic, and dereference it to get the number of 3, which is we pushed into the stack previously, and then we store into the EAX, and then we add it to 1. Now the EAX is 4, and then we pop the EBP, which means EBP will go back to its old place. And then finally we return, and we get the return address here so that we know what is next step after we return. And finally, we'll make another space for ESP so that we can be ready to push the arguments for printf, right? And then okay, I think this is also a key step because we want to, actually the return address of not the return address, but the return value of worker is stored in EAX, and we want to push this return address here. The reason is that in the printf, the third argument is just the return value of worker, right? So we push that first, and then we push the string, and then finally we push 1, and finally we push the return address of printf. Then we call printf, and that's it. Okay, does that look clear? Okay, any questions so far?
Is it a number of your argument decided by the compiler?
That's a good question. I think so, yeah. Because if you have like 10 arguments, then the compiler will, I think it will look at how many arguments you take and then make space correspondingly. Okay. So that's totally due to the compiler, yeah. So that's why when you make space here, so here it just makes like the 16 extra space. I think that's totally due to the compiler. For different compiler, I think this value can change. Yeah, make space. But I think compiler will always make sure that all the arguments you push will be, yeah, the stack is already can hold the number of the arguments you're pushing. Yeah, good question. Any more questions? Okay, so what we know from this demo. So first is the arguments of the function are pushed into the call stack in the reverse order. Right? So for printf, for example, we always push the last first, the first last. Okay, and finally, after we push all these arguments, we'll push the return address. The reason is that when we return, we always, the call stack will pop, and then we'll know where are we after return, okay, the next instruction. Another thing is that when you essentially execute your function, the arguments of your function can be retrieved or can be accessed from the pointer arithmetic of EBP. Okay? And then finally, which is very important, the return value. Okay, previously it's return address. Okay, return address is always pushed at last and popped first. Yeah, that's essentially the property of the stack. And the return value is actually stored in a general purpose register. For example, the EAX. Okay, the number 4 is always stored into EAX, so that when you want to return, you will refer to the EX, and then you know what is the return value is. Okay, then we have some reminiscence. As you can still remember, fork will return two values, right? If it returns to 0, then it means it's a child process. If it returns to a PID, that means it's a parent process. Of course, if it fails, then it's -1. Let's assume it doesn't fail. Then it returns two values. Then how are we handling this particular case under the hood? So again, let's look at our good friend, not good friend. Just let's see what xv6 does in fork. Okay. Oh, sorry. Okay, here. Copy a bunch of things, and can you see here? Okay, so this is a comment. Clear EX so that fork returns 0 in the child. So it's very simple, right? As we mentioned, the return value is always stored in EX. So if we manually set the EX of the, okay, NP is the child process, okay? The child process. If we manually set the EX of the child process to be 0, it's kind of hacking, right? Then the child process will, of course, return 0 from fork. And for the usual parent process, it just returns PID. And when you return PID under the hood, the EX of the parent process will be just PID. Okay, so that's just simple. You just manually change EX, and then you return 0 from the child. Okay. Okay, so I think this is the demonstration of a very simple code, but I think we just help you go through the calling convention, refresh the memory. But why are we doing that? Again, because we want to implement clone. Okay, so here's another demo. So essentially, this is just like a kind of the test case, the simplest test case to test if clone works. So when you finish your implementation, you will call clone like this, which is as expected. Now worker is just a routine will be executed in the thread, right? And in worker, it does a very simple thing, just updates the argument, the value that the argument points to, increments by 1, and then that's it. And now again, we want to do another GDB step-by-step to see what happens for this. But for this time, I think we should be in a faster pace, because I think you should be getting more familiar after the first demonstration. Okay. Okay, let's just. Oh, I think, yeah, there's another one. Sorry, it's here. Yeah. Now again, because we want to debug into the user program, so we just add symbol file. And so now it's demo2. Again, set the beginning address. Okay, now we want to break at should.c, which line? Okay, let's just break into line 11. Okay, now here we run demo 2. Okay, now we are at clone, right? Here. Okay, see? Again, this is very familiar, right? The parenthesis means we want to move the value at 8 above the EBP and then put into EX, okay? Now we can take a look at what EBP is pointing at. So at this address, so we want to dereference it to see what the value is stored. 8 above this. So essentially, I think this is an address of argument, right? Because this is a clone, this is a function, right? We always push the argument in the reverse order, so we want to push this first. So let's just check what is the address of argument. No. What about worker? Sorry. Okay, I think I'll just go to the. I don't think this one is the correct one. Okay, I think this is the correct one. Yeah, I somehow don't quite understand why you have to continue it twice. But anyway, so here is where we should look at. So now we push the 2D04 to the stack. So what is the 2D04? It's exactly here, right? The address of the argument, right? Here. So we push the argument into the stack. And then we push worker, which is 2048, right? 2048 is, yeah, here, right? We push them in the reverse order, and then we call clone. And I think now we can step to the next. Then clone is a syscall, right? And we'll in a system call. But at the same time, you can see that what is the value of, okay, let's see where is the ESP now. Okay, so this is ESP. And let's see, what is the value here? $2023. So what is this value again? The return address, right? Because we push the argument into stack and push the worker into stack, and then we call. Call means we push the return address into stack, right? So we finish call, then we get the ESP now is pointing to the return address. So is it 2023? Let's just look, have a look. obj dump fs demo 2, right? 2023. Yeah, I found that. Here. This is the return address, which is right below the clone, right? Calling clone will return here. Okay, still consistent. Now, if we step further, then we'll do the system call. Okay, because I have already implemented the clone here, so we will not debug the clone itself, but I will still set up the clone breakpoint, but I will not step into it. Okay, I will finish, and so you can see the return address of clone is 4. The 4 is exactly what just because in clone we mentioned that the return address return value of clone is actually the PID of the new thread. So 4 is actually the PID of the new thread. The parent process is got 3, right? And shell is got 2. So 4 is assigned to the new thread. So after we call clone, the new process, new thread is generated, it's created, and it's placed into the P table, and it's got a PID of 4. So if we break into worker, which is what the thread will do, right? And then we continue. Now we're in the worker. So right now, when we break into worker, it means this is the thread that is running, not the parent anymore, right? Because parent is only creating the thread by calling clone. But in the real thing, the worker is just executed by the thread, okay? So when we break into worker, it means we are now in the thread. So if you look at the register or something like that, all the information from here should belong to the worker, or should belong to the thread instead of the parent. Okay. So when you look at the ESP, see, this value is much lower than what we've seen originally, because I think you still remember for the parent process, yeah, it's like 9FF, right? It's very high. It's almost close to the user top. But here, it's a relatively lower value. It's got 9DFF4. So as you can see from here, this is the user top, and all the parent process, in the parent process, all the stack like ESP, EVP will reside in this regime, right? However, in the thread which we created just now, the stack will be here. So 2 pages, so it's so this line is exactly 9F000, right? So 9F0, so, oh sorry, 9D000. So D is 13, right? So this is exactly the highest address of the stack of thread 1. So that's why here we have a, sorry, it's not. So what is A000 minus 2000? It should be E, right? Okay, so it should, the highest, so sorry, this line should be 9E000, okay? So something below it should be 9DFF something, okay? So you can do the math, but you can also verify. So the ESP right now should already be in the regime of the first thread, the stack of the first thread, okay? And you can also see BP, yeah, it's pointing at the same place because yeah. And then, what about EIP? EIP is just the address of the worker, right? 204B. So how does the thread know it will execute this instruction, or the EIP will point to this address. There's no magic here. There's no automation. You have to do that, right? Just like just now in fork, we manually set the EAX to 0, and then the child process just returns 0. That's it. If you don't set up EX equals 0, then the child process will still return PID. So for here, there's no automatic magic. You have to manually set up. So you have to manually tell the thread that, hey, you should go to which line, or you should go to which instruction. And for here, it's exactly this address. You should assign this address to the EIP of the thread, so that the thread knows where to go. That's the key here. Okay. So if you don't set it up, the child thread will not know which instruction to follow in the next step. Okay, so you have to manually set up somehow in the clone so that the thread will know. Okay, this is the key that your code will work. Yeah, I think that's it. Okay, the final thing is, since this is a worker is a function, right? And a function will always return. However, this function in the thread is slightly tricky here because we don't want it return. So let's go back to the C code. Sorry. So here, when you call clone, right, the parent process will just create another thread, and then the thread will be placed into the P table. And once you tell or you point the EIP of the thread to a specific address, and then your thread will know, okay, my next instruction is here, and then your child thread will execute this function. Does that make sense? Once it finishes this function, because it's a void, so it returns nothing. By theory, it should return to clone, right? But right now, we don't want it to return. What do we want it to do? Because this is essentially when the thread should end or should be killed, should terminate it. Meaning, once it finishes worker, then I don't want it to return. I want it to be terminated. Then how do we realize that? We still should assign a return address to this thread. But different from previous scenario where we store the return address of the next instruction, but right now we should assign it a fake return address. That's exactly what we mean in the instruction, in the specification. We should assign a fake return PC, which is -1 or 0x followed by 8 Fs. We should assign this fake address. And what happens after we sign it? So we can look at this here. So this, we are still at worker, right? Okay, we're at worker. Now we just finish this worker. Yeah, sorry, I shouldn't use finish. Okay, never mind. I will just try again. Yeah, I should use step by step, but okay, sorry. This is okay, now we will finish. Okay, now we run again, then we generate a new thread, which is PID 6. That makes sense, right? And then we return, and then we next. Okay, now we are in worker. Okay, now let's use SI, step by step. Okay, now at this step, let's look at ESP. Okay, that's fine. EBP, that's fine. EIP. Okay, still in worker. I think there's nothing. That's fine. I don't want to. Yeah, because EX is changed somehow here, but yeah, we don't track it, so we don't want to worry about EX. And now we go to next step. So we pop EBP so that EBP will go back. Okay, so we return. Let's see ESP again, EBP again. That's totally fine. See, here. So we just return, right? Normally, when we return, we'll go back to the next instruction of the caller, right? So here, as you can remember, when we return, the next is this instruction is essentially stored in this address, right? This address is essentially pointing to this instruction. So when we return, we know we should do the next instruction. But now we don't want to return, and we want to assign it to the fake address. That is why we have this. So when it returns, it gets to a fake return address. And then system will don't. Of course, this address is invalid, right? It's unmapped. So you can try to dereference this address. So -1 is equivalent to this. It's not accessible. So what will happen when you manually go to this address? What will happen? Something bad, right? And once something bad happens, what will system do? Right, exactly, trap, right? So the system will trap. And this is, I think when you do p4b, you see a lot of trap 14 error or something. 14 is actually the trap number of page fault. So essentially, this is just a page fault. And then the trap system will trap this, and system will handle that. And when you see the trap.c, the trap handler will just kill this process. So when we say a function doesn't return, we just redirect this function to a bad address, which is -1 here, and then system discovers it, oh, that's bad address, and the page fault is raised, and then we just, the trap handler will just kill this process. So that's exactly what we'll do here, okay? So when you go on, it will just jump to the trap handler. Yeah, a piece of bad things happen. Okay, calls trap. And then it will see if the trap number is system call. System call is 64, right? Yeah, but right now it's not 64, it's 14. Yeah, you can just print tf trap number. Exactly, it's 14 means it's page fault. So it doesn't go to this if. So no, it's just comparing. Okay, switch trap number. I'll just use next. Okay, so this is exactly what we'll do. So the RCR2 is just to get the address that's system got stuck, and then see, okay, it's -1, then the process will be killed. Yeah. And this, then thread 6, right? The IP ID of 6 will be killed, but the parent will not be killed, right? They have just Although they share the same address space, but in the p table, they have different entries, right? So number 6 is killed, but number 4 is still there. So that's exactly what we will do here. So I think it looks very familiar for you guys, right? This fake return address. Can you still remember where you've seen that? Exec, right? Here. Here we still have a fake return PC. So exec here is very similar to the clone, what we are handling in this project. So if you want to have a better knowledge of why is this fake return address, you can look at the exec more. But I think today the demonstration too is, I think it's relatively more showing what is behind, under the hood, okay? So what is exec doing? I think for last time, Xiangjing also have a very detailed debugging step by step of exec.c. And here we just, again, store the arguments in a reverse order. And finally, we store the return address here. So it's very similar. So this is what exec do. But for the clone you are implementing, it should be way easier than this part. I think all you need to handle is just this part. Because for here, the exec has to also take care of the main function. But in clone, you don't need to worry about main because it's just execute a particular function you define, which is FCN, right? So there's no main in thread. So you don't need to worry about this. All you need to do is just properly push your arguments in the correct order, and then correctly push your return PC, which is this -1. And then I think you are ready to go. Oh, by the way, another piece is that just now I mentioned, you have to set up your EIP correctly, because if you don't set up the EIP of your thread, then your thread will not know where to execute, and it will not know, oh, I should execute the worker. Okay, so that's the key thing you should take care about.
So the flexibility if RCR2 equals 0x.
You mean this one?
Yeah.
Actually, it's not in your version.
Yeah.
It's so you need to handle that. But actually, I've already, yeah. Okay. I think that's it for the exec. So I think, so right now I think you should have a very high level or conceptual ideas of what clone is doing. Okay. So I think here's a more general guidance. So for clone, it's essentially just analogous to a fork plus a exec. So when you create a new process, you fork and then you exec. It's in a separate step, right? But for clone, it's actually compressed into one, which is just clone. So basically, you clone a thread first, put it in the p table, and then you properly set up the arguments of the routine of the thread, and then you properly set up the EIP of the thread, properly set up the fake return address, and then you're ready to go. Yeah. And yeah, I think we can also spend some time looking at the fork, although I think you have already looked at it many times, but I just want to show you here. So here, alloc proc essentially just allocating a new entry in the p table, right? So that should be the same for thread. And here it's just copying the address space of the parent. But for thread, you have to think about that. Is this the same, or you should somehow change this? And here, set up a bunch of things. That's fine. Yeah, I think fork. You really need to think about this according to the difference of process versus thread. Okay? I shouldn't tell you more because, yeah, I think I have reviewed like 70% of what clone should look like. So, yeah, you should have spent some time to really understand what it's. But I think after today's discussion, it should be helpful, hopefully. And finally, I want to briefly talk about the condition variables. So I think as you read through the specifications, after you implement it correctly, the clone and join, you've created the thread. Then we want to also implementing the 3 pieces of the resources, right? The first one is this simple spin lock, which I think is much easier because I think in your midterm 2, you have already tried to do that in your exam. So you can just put that using the simple hardware, which is exchange in XV6. And that's very easy to handle. Semaphore is also easy as long as you finished implementing lock and condition variables, right? Because in class we have already showed you how to correctly implement semaphores based on those 2 pieces. The only challenging thing is how to implement condition variables in XV6. So condition variables has basically 2 routines. One is count weight, the other is count signal. So according to the definition, yeah, you can just implement the condition variable, the routines, according to the definition of what the routine does exactly. But to give you more hints, I think you can just refer to another 2 existing system calls in XV6, which is sleep and wake up. So I think sleep is just analogous to count weight, and wake up is analogous to count signal. So let's just take a few minutes to look at what sleep does exactly. No, not us. Okay, sleep is here. So essentially, it's got 2 arguments. The second one is easy, just a spin lock in the XV6. And here, Chan, what is this argument? Have you had idea of that? So if you look at the PCB, so in proc, it's already got a Chan. So it's actually short for channel, but it's just a naming. So it just signal or tell sleep sleep on a specific channel. So say Chan can be 1, 2, 3, 4. If you sleep on 1, then 2, 3, 4 will not be affected. So it's just like a indicator to distinguish different channels, something like that. And this is very similar to condition variables. So you can see here, count weight also takes in 2 arguments. The second one is the lock, which is similar to this guy. And there's a count T type of CV, which you can approximate it with Chan here. So we just look at what sleep does here. Sorry, I should not show you here. But yeah, you should try to look at what sleep does and try to learn from sleep and then try to implement the count weight, okay? So I think the key idea is here, when you go to sleep, you should set up, you should remember this channel, and then you update this proc state to sleep, and then you call the scheduler. That's basically what sleep does. And if you look at the definition of condition variable, the first step, you should assert lock is required. Okay, and then you put caller to sleep on specific channel. So here is on specific CV. Right? So that's why we have like in the producer consumer problems, we have like 2 CVs, right? We should make them sleep or wait on different channels so that we will not wake up an arbitrary thread. Okay, so it's kind of you have to specify which channel to sleep on. That's exactly what is CV here. And then we release the lock. Yeah, that's very easy. Okay, and then finally we wait lock to be released again. So this wait, you can just use the simple string waiting here, and then reacquire the lock. So if you just lost, you just look at what sleep does, and I think you can have a very good idea of how to implement this. And for comp signal, I think it's much easier because you can also look at wake up, which is just so wake up from sleep, right? And condition count signal from count wait. So they're just in pairs. And here, when you look at wake up, it's very simple. I think just one line. Yeah, just one line. Lock the p table and call wake up 1. And wake up 1 is also very simple. It's just scan through the p table and find the sleeping process. And the more important one is it has to find a matching channel, and then set the state from sleeping to runnable. So that's the key here. So you cannot wake up arbitrary process, right? You have to wake up a specific process which is specified in the channel. So is the count wait or count signal. Okay, so I think that should be clear. And that's it, I think, basically. So any questions so far? Okay. You mean when a thread terminates? Sure, you should release that. Why is that? Because so here we only allow at most 8 threads to be run concurrently, right? Not including the parent. So the parent itself is actually another thread, but the main thread can clone another 8 threads that run concurrently, which means each process or thread takes up 2 pages, right? So altogether 18 pages should be, that's the maximum address space to take up. But right now, if a certain a certain thread terminates, for example, if thread 1 terminates, then this chunk of memory, this page, should be released, so that later more new threads can enter. So I think this idea is very similar to 3A again, right? So in 3A you have 63 clients, right, in a shared memory, and here you have 8 threads. Yeah, and they just reside in this region. And if a specific thread exits or terminates, then you should clean up this region. And where did you clean up? You should clean up the corresponding stack at join. I think here we mentioned. So when a thread finishes, the join, this routine, should reset the stack. Yeah, so that later thread can reuse this. Okay, you should not have a memory leak. So it's just like a free. So if you don't reset it, it's kind of memory leak. Yeah. And oh, by the way, there are some italic fonts here, which is some updates from the day that was first released. Some updates, and the strike means that is not very correct. This is some updates. If you have read it a long time, no. If you read it the first day and you didn't double check that, you should do check it again because there are some updates. Probably there are more updates later. People have more questions about some. If something is not very clear, yeah. So just keep on top of it, okay? Yeah, because it will be updated somehow. And yeah, another thing, tiny thing is that you have to note that join here does not take any arguments. And some students are already asking me why it doesn't take any arguments. That's because it will just wait a specific child thread. And if there are multiple child threads, and it will just wait the first thread that's finished or that's terminated. So for example, if process A clones thread B and C, now A calls join. A will wait for whichever thread finishes first. So if C finishes first, then it's just A just waits for C, and then immediately the join will return the PID of C, and B, if it's running, then it's running. But if it's terminated somehow and no one is joining B, then actually it will be in a zombie state. It's not, no one is cleaning it up, and you will have some output from the shell. But you should always make sure that if you clone the threads for n times, then you should correspondingly join n times. That's completely impaired. Okay. But if you join more times, then you should return -1 because there are no more threads that are not finished. So you should return -1. You didn't find any threads that needs to be joined or waited. So I think join is analogous to wait. So to implement join, you should take a look at what wait is doing. Okay. So I think that's basically it for this discussion. If you have further questions, you can come, and if not, we'll meet you guys in the lab. Okay? You have more questions?
Yeah. Question still about the argument because for the function clone, the first argument is function pointer, right?
Yeah.
In our case, it's worker. However, what if the worker has more than one argument?
That's a good question. We'll not do that. Meaning, worker will always only have one argument. That is a pointer. And you can look at, again, you can look at the menu of pthread. Great. So it's completely the same, right? So it only takes in one argument. It will not take more. So it's only taking a pointer. So if you really want to pass more arguments, then you should have an array. And this pointer points to the array. Yeah, that's the only way you should do that. But in our test case, we will only have one argument. Okay. Yeah, it's just the same with pthread create. So this is slightly different from exec, right? Exec can take you have argc and argv. Argv is an array, and argc is the number of the items in the argv. But here for the clone, you should only pass in one argument. Okay. Okay. If not question, we'll just call it a day and.